Telecommunication and radio communication is such a huge part of modern society that it's important to understand some of the principles that govern how we can transmit a variety of different pieces of information over the same medium. In this case, the airwaves or the fiber optic cables that run underground. And so in order to understand that, it's useful to go through a little schematic diagram of what happens when a signal gets modulated, transmitted, demodulated, and filtered, so we can understand the basic building blocks of a telecommunication system. Okay, so let's start with the idea that we've got a signal that we want to transmit. I'll call that, it's probably some sort of voltage, since we're typically doing this electronically, so I'll call that V sub sig. And it's going to have some waveform in the time domain. So think of this as a piece of music that's being recorded by a microphone. This might represent a pressure versus time. And we want to transmit that as a radio broadcast. So that signal is one of many that are going to be transmitted over the air. And we want the listener to be able to choose which station they're listening to. And we wouldn't want to just simply broadcast this signal directly for a variety of reasons. One is that the frequencies at which the signal are at are not ones that are particularly conducive to small antennas that you might have in a car or on a radio. But also because if we just transmit that signal directly, then it would interfere with any other channels that are being broadcast as well. So in order to avoid that, we use a technique called demodulation, where we have what's called a carrier wave. And a carrier wave is just a sinusoidal signal. I'll try to avoid using the term signal for this. It's a sinusoidal waveform that has a well-defined frequency, and that will define the center of the channel of information that this signal will be transmitted on. So in order to follow through all the steps in the modulation and demodulation scheme, it's really useful to look at the frequency components of these signals. So if I take the Fourier transform of this signal, I can plot the spectral content. And a typical signal is going to have most of its spectral content near DC, with less and less at higher and higher frequencies. And depending on the type of signal, we'll get different characteristic shapes for this signal spectrum. If it's an audio signal, we expect most of the information to be between 20 hertz and 20 kilohertz. And in practice, most radio transmissions or audio transmissions don't transmit up to 20 kilohertz, but limit the bandwidth somewhat below that. Likewise, we can look at the frequency domain representation of our carrier wave. So if this is zero frequency, a sine wave has a Fourier transform that is a delta function at plus and minus the frequency of the carrier wave. And so if we want to take the information contained in this signal and move it in the frequency spectrum to be centered around the channel corresponding to this carrier wave, we do that by modulating the signal. So we can take our signal, and in this case, modulation will be multiplication by our carrier wave. And in the time domain, what that's going to look like is our original signal will form an envelope over this higher frequency carrier wave. So we'll still have these sinusoidal oscillations that we had at the carrier frequency, but now their amplitude is going to be modulated by this, function here. Right, so this represents amplitude modulation. And the ideas that we're presenting here, we'll look at amplitude modulation, but they're very similar for frequency or phase modulation as well. Okay, so this is the time domain. That's not the most useful representation. If instead we look at the Fourier transform of this, the spectrum of this, that's going to be the convolution of my signal and my carrier. Right? When you multiply two signals in the time domain, that's equivalent to convolving their frequency components, the frequency spectrum. And so that means we take this spectrum and we shift it by plus the carrier frequency and minus the carrier frequency. That's what happens when we do the convolution of these two functions. And I'm drawing this where the carrier frequency is much higher than the frequency bandwidth of my signal. And so the signal spectrum essentially gets shifted up and down so that it's centered not at 0, but at plus and minus the carrier frequency. And now, if there's a limit to the frequency content of the signal, if I can say that the signal only contains frequencies up to a certain amount, then I can sort of block off this region of the spectrum and call that one channel. And say that all the information contained in my signal will fit within that channel. And of course, the value there is that I can repeat this process with a different carrier that's at a different frequency. So let me consider, I'll sort of exaggerate this, but a lower frequency carrier is going to have the same frequency spectrum, but the center frequency is going to be less. And therefore, if I have a different signal, maybe a different radio station that has a slightly different spectrum, that gets shifted by a different amount and sits over here at a different center frequency than my original signal. So I've essentially now encoded two different signals. So I can start with the time domain representation of these two different signals. And I've encoded them on some waveform that I'm going to transmit such that the information contained in those two signals is at different frequency components, or the information is contained in different frequency regions of the spectrum of the information that I will transmit. Okay, so this modulated signal here is what gets transmitted. So this is the transmitted signal. And by doing it this way, I can encode many different channels on this transmitted signal, and the information can be separated and later recovered independently of what's in the other channels. It is also useful to do this modulation because I can choose the frequency region at which the information is transmitted. In the case of FM radio, we choose frequencies that are around 100 megahertz, and those are chosen more or less because the optimal length of a quarter wave dipole antenna to detune them is about 1 meter, and that fits nicely on a car or in a telescoping antenna on a radio. And they can also be chosen so that they don't interfere with other things. So you can have your signal transmit in a region that's not going to interfere with your Wi-Fi signals or your FM radio or your walkie-talkies or your cell phone reception. Okay, so this is what gets transmitted over the air or through an optical fiber or through our communications medium. On the other end, we want to be able to decode the information contained in one particular channel and recover one of the original signals that's being transmitted. And so to do that, we need a demodulation signal. Just like we had this carrier wave for modulating, we need to choose a demodulation signal that will be a sine wave at the frequency of the carrier that we're trying to decode. So at the center frequency of the channel we're interested in tuning in. So I'll call this V sub D. And in the frequency domain, sine wave, so it's going to have spectral components at plus and minus f sub d. So the process of demodulation is just like the process of modulation. We take our demodulation signal and we multiply it by the signal that we're receiving, which I was calling the transmitted signal. And so just like the process of multiplication by a carrier up here caused the frequency component of our signal to get shifted by the carrier frequency when we did this convolution in the frequency space, now our transmitted signal is going to have its frequency spectrum shifted by the frequency of the demodulation. And so if we choose the frequency of the demodulation correctly, then we can shift the components that are centered in one channel back to DC, okay, back to the center frequency that they originally had before they were modulated. And of course, we're also shifting up and down, and we're shifting the entire transmitted signal, not just the channel that we care about. So this channel is going to get shifted to here, and this channel gets shifted to there, and also goes in the other direction. And so what we end up with is a frequency spectrum. So if I plot this in frequency space, that has the original signal that we care about, its frequency spectrum reproduced, centered around zero frequency. But then it's also got the neighboring channels frequency spectrum, and I'll draw them in a separate color so we can keep them distinguished. Around that, as well as what we call an alias, or a reproduction of this original frequency spectrum at a shifted frequency that corresponds to this signal getting shifted both up and down. And likewise, some additional alias from the other channels. So we have this really complicated and full frequency spectrum, which has our original signal at its appropriate frequency, but has all this other junk. And so the way we deal with that is to filter out the other junk. Right? We want to put in a low-pass filter that essentially blocks out this other stuff. Okay, so a low-pass filter is equivalent to averaging. So let's now average this in time, and we'll call this our output signal. So it's just our demodulated signal, low-pass filtered. And we choose the cutoff frequency of this low-pass filter such that it passes spectral content within my desired channel, but it blocks the neighboring channels. Okay, so the knee of this low-pass filter should be determined by the width of our frequency channels. Those frequency channels' width should be determined by the width of the spectral content we want to communicate. If this is an audio waveform that has spectral content up to 20 kilohertz, then we might want 20 kilohertz wide channels, actually 40 kilohertz, 20 on each side, and then we want our low-pass filter to be at plus and minus 20 kilohertz. Knowing the frequency corresponds to, of the low-pass filter, that corresponds to the integration time. So 1 over that frequency would give us the integration time that we have here mathematically. And that's the idea. Once we've done that filtering, our output signals in frequency space is going to be a reproduction of our input signal spectrum. Okay, and that's in frequency space. In the time domain, if we have the same spectrum, we're going to have the same signal. So this is the basic idea behind modern communications, allowing multiple channels to be broadcast over a single medium. It's used in radio broadcasts, as I mentioned, but it's also used for transmitting data over fiber optics or over microwave frequencies for cell phone transmission and things like that.